Hello everyone, today we're going to solve one of the important problem that's going to challenge your understanding about binary search tree. The problem is that valid binary search tree. So without wasting much time, let's get started. So what is the problem statement is that you're going to get a tree. So you're going to get a tree and you just have to tell whether the given tree is a valid binary search tree or not. So before moving forward, let's have a glance about binary search tree. So what does binary search tree mean? So if you take any particular node in a binary search tree, all the value to its left side are going to be less than the node, and all the value to its right side are going to be greater than the node. I hope you guys understand or remembered about binary search tree. Now let's talk about the problem statement. The problem statement is pretty simple. So you're going to get a tree like this tree and just need to apply all the property of binary search tree and tell whether it is valid or not. Just return true or false. That's it. It's pretty simple problem statement. Now let's think about the solution which everybody thinks. So which is starting with the root node. By looking at this context, we are going to use DFS only. So let's apply the DFS property. So let's do for right side, and we're just checking whether 5 is less than 3. Yeah, it does. So it's okay. It's valid. Now there is no more node on the left side. So all the things has been done. Now let's go for the right side. Let's check whether 7 is greater than 5. Yeah, it does. No problem. Now let's move to the left side node. Tell me, and whether 4 is less than the 7. Yeah, it does. Everything is done. Now let's move to the 8. 7 is less than 8. Yeah, it does. So just tell me guys whether this is a valid binary search tree or not. Tell me. No, it doesn't. It's not a valid tree. The reason because if you look at 4, 4 should never present on a right side. If you remember the property, right side will have always the greater value than the root. It might pass in this particular case because 7 is greater than 4. But if you look at the property of BST, any particular node, all the value must be greater than. But in this case, it fails. The 4 should lies on the left of 5. So this is not a valid binary tree. The brute force is pretty simple, guys. What we are going to do is that we are going to take a number 5 or any node. We are going to we are going to take a 5 and we're going to compare all the value in the left side is less than or not, less than 5 or not. We're going to check it. And to the right element, what we're going to do is that whether 5 is less than the right element or not. We will do this for every particular node. So once we did this, yeah, it's fine. So we're going to apply the same thing for 7 as well. So we're going to check for 7. We're going to compare 7 with 4, whether it's less than or not. Same for this particular case. If you look at the time complexity, it's going to take big O of n into n, because for every node, we are visiting all other nodes. If you take this 5, we're going to take all the node. And if you take 7 as well, we are going to visit all the nodes. The time complexity is going to be big O of n square. So can we do better? Tell me guys, can we do it better? Yeah, we could do it better. Let's see the optimal solution for this one. I'm going to take a little big example for better demonstration. So let's think about the property of binary search tree. What does it tell? So left side value is going to be lesser and right side value is going to be greater, right? We can utilize this and we can make some optimal solution which is going to be better than brute force one. So the trick is going to be that. So let's put a range. Okay, we are going to do a range. So tell me, what is the range for the root node? Is there any constraint? Tell me guys, is there any constraint for a root node to be followed? Is there? No, there's no constraint to be followed for the root node. But if you take for this particular node, we have some constraint or we have some range for it. The constraint should be like whatever number on a left side for this 14, it must be less than. Okay, it must be less than. All the value must be less than 14. So there's a constraint for this. So root can be from the range from negative infinity to positive infinity. Am I right? It can be any value. There's no constraint applied for the root node. So let's keep root node constraint is going to be from negative infinity to the positive infinity. So let me write it down. So we are going to do a recursion base. So instead of having a recursion stack, so let's do a new approach by using call stack tree or a recursion tree. So recursion tree is a good way to visualize things. So let me draw the recursion tree, guys. So initially we are going to start a recursion with the root node and the lower value, the lower bound and the upper bound. Okay, these are our states for the recursion. So initially we are going to have the root, which is 14, and what is the lower bound? It's going to be negative infinity. Now what is the upper bound? It's going to be positive infinity. Now we are going to start the recursion. What is going to be the cases? Two cases. The one case is going to be left children and the right children. So now for left children, the node is going to be 8. Am I right? Now we have to decide the boundaries. Now tell me, guys. So when we are moving to the left children, which boundary we need to change? Tell me which we need to change. Just look at this and tell me we have to change whether the lower boundary or upper boundary. If you observe carefully, your answer is going to be the upper boundary. The reason because if you look at the constraint, it will look like this. So 8 must be greater than the negative infinity, but it should be less than 14. So what does change right now? The upper boundary change. So always keep in mind that for all left search, we are going to update higher boundary. And for all of the right search, we are going to change the lower boundary. Now, if you write similarly for this particular node, how does it look? It's pretty simple. What is the left property? All the node must be greater than the root node. So the equation will look like 17 must be greater than 14 and it must be less than positive infinity. Am I right? So initially our things will look like 14 comma negative infinity positive infinity. This is the lower bound, this is the upper bound. So when you come this particular place, we are just changing the upper bound only, but when you come to the right child, we are changing the lower bound. I hope you guys understand how this searching works. Now let's continue the dry run. Now you guys are going to tell me what should be the lower bound upper boundary. Okay, you can take pen and paper or you can just tell me what is going to be the lower and upper boundary. So now we are going to do search on the left. So which thing we need to change? Tell me. Upper boundary, right? So the lower boundary is going to be still the same and upper boundary is going to be the parent value, the root value, which is 14. And now we have two cases again, left and right. Let's do left and right. So next node is going to be 7, and for right search, what need to be changed? Upper bound. So let's do it. The lower bound is going to be still same. The upper bound is going to be 7. Sorry, the upper bound is going to be 8, the root value. And what we have to do for the right? Let me write the node value. It's going to be 10. And for the right node, we are going to change the lower boundary. So what is the lower boundary? Tell me, guys. The root value. And upper bound is going to be the 14, same as it is. So I think we just reached the leaf node. Now we have to do the check. Check very simple, whether it is valid or not. So our current node is 7, which is greater than negative infinity. Yeah, it does. The if condition will look like this, guys. Let me write the if condition. It will look like root dot value must be greater than the lower boundary. Am I right? Must be greater than the lower boundary, and it must be less than the upper boundary. It must be strictly less, not less than or equal to or greater than or equal to. It must be strictly less than the upper bound. So root dot value must be less than the higher value. If it passes, which means this particular node is valid. Now apply and tell me, guys, whether this is true or false. Apply to this case. 7 is greater than negative infinity and 7 is less than 8. It pass. So let's put true over here. And now let's apply the same case for this particular recursion. So 10 is greater than 8. Yeah, it does. And 10 is less than 14. This is, remember, this is lower boundary, this is upper boundary. As it pass, so let me put true over there. And the condition is going to be AND. If both the things are true, we are going to return true to the parent. So this is going to return true to 8. Now we just finished the iteration of all the left node. Now we are going to do for the right node as well. So let's continue the process. So next thing will be 17. And now you guys going to tell me what is going to be lower and what is upper bound for this. For 17, what is the lower bound? It is 14. Now what is the upper bound? It's going to be the positive infinity. Now we have to perform left and right as well, right? So what is the left for it? Left node is going to be 15. And tell me what is the lower bound? It's going to be still 14. And what is the upper bound, guys? It's going to be 17. Pretty good. I think you're doing good so far. Now we have to do it for the right side as well. Let's do. The right value is going to be 19. And what is the lower bound? Lower bound is 14. And what is the upper bound, guys? Now what is the lower bound, guys? It's going to be 17. And the upper bound is going to be the positive infinity. So always remember, for right search, we need to change the lower boundary. And for the left search, we need to change the upper boundary. So let's continue the process. So again, we have split for 19 as well. Let's do it. So 19 as 18. And for left node, we are going to change the upper bound. So lower bound still stays the same and upper bound is going to change for 19. And we are going to check do for this as well, which is 20. For 20 right side, we are going to change the lower bound. So lower bound is going to be 19 and the upper bound is going to be positive infinity. Now let's apply this condition and check whether it's true or false. Now let's start with this particular thing. Tell me, guys, whether 18 is greater than 17 and less than 19. Yeah, it does. So true. Now let's do it for this as well. Now tell me 20 is greater than 19 and less than positive infinity. Yeah, it does. So it's going to be true as well. What is true and true? It is true. So for this particular node, our value is going to be true. Now let's do for this particular case. Now tell me 15 is greater than 14. Yeah, it does. And whether 15 is less than 17. Yeah, it does. So this also going to return true value. Now what is true and true? Same, true. So now we have found all the cases. Now we have to do for the final node. Now tell me what is true and true. Finally, this is going to return a true, which means a given binary search tree is a valid. Now if you apply the same thing for this particular node, how does it will look like? It's going to look like this, guys. So this is valid, right? This is valid. This is going to return true. But if you look at this particular node, things will change a little bit. So this is true, but this is false, because if you apply the condition, the boundary will look like this. The boundary will look like 4 comma, what is the lower bound? Lower bound is going to be 7 and the upper bound is going to be infinity. The lower bound is going to be 5 and what is the upper bound? 7. So does this satisfy whether 4 is greater than 5? No, it doesn't. So it fails. So we get false over there. And what is false and true? It's going to return false. And what is false and true? Again, this is going to return false over there, which means the given BST is not a valid. I hope you guys understand this problem very well. Now let's quickly code this up. So let's start the coding, guys. It's going to be pretty simple, very easy. So let's write the DFS function. So remember, what are the state? State is going to be root and lower bound as well as the higher bound, right? Now what is the base case? So base case is nothing but if there is no root, then it's true, right? If there is no node, we are going to return a true. So if not a root, simply return true, because nothing cannot be, I mean, if there is nothing, we cannot tell it as a false, we should tell it as a true. So if there is no node, we are going to simply return true over there. Now what is the next step? We have to check the condition. If you remember, the condition is that the root value must be greater than the lower bound and it must be less than the higher value or upper bound. So let me write the case for it. If root dot val is greater than low and root dot val is less than the high, so if it does, we are going to proceed for the next step, right? What's the next step? Next step is that we have to check for the right, we have to check for the left. So I'm just going to negate this statement. Instead of true, I'm going to negate it. So if it's not satisfy this particular place, I can simply return false over there, right? Now I can freely write the remaining test cases. I can write the splitting in this particular position itself, but it's the best way to negate whatever case at the beginning so that we can write the remaining logic very freely. So just simply negate it, and if it's not satisfied, we are just simply going to return false over there. So if it's satisfied, what do we have to do? We have to do search on the left and right. So let me write recursion for that. So the root is going to be root dot left. What is the lower bound? Lower bound still stays the same. For the left side, the lower bound is going to be stays the same, but the upper bound is going to get changed. So upper bound is going to be root dot value. If you guessed it correctly, well and good. And now let's do it for right side as well. So root dot right and lower bound is going to be good. Now we have to change the lower bound as well, right? So let's do that. So the lower bound is going to be root dot val. For the upper bound, we are not going to change anything. It's going to be still stays the same, high. Now at last, we can simply start a recursion with the root node. The initial lower bound is going to be the negative infinity. So in Python, it should be like this. And the upper bound is going to be the positive infinity. And that's it, guys. It's pretty simple code, right? Let me submit it. I hope it passed all the test cases. Yeah, it does. Thanks for watching till this year, guys. We'll meet again in one more video. Until then, bye.